Okay everybody, we have 3 functions left before we're done with this lab, and so let's jump right into it. We're going to start with calculate return. Calculate return takes an experience we had from the rollout and puts it into memory. That's literally all it does. It copies it element for element, except for the last thing. The last element in the tuple that comes out of the rollout is the reward that we got. We want to transfer that reward into a return before we put it into the memory. Okay, so let me draw a picture of this. What I'm saying is, you have this big long list of memories called memory, and then you have a shorter list of memories called the rollout. And you're gonna the rollout represents one play through the game, and these lists have the same columns, except for this column right here is the reward, and before we put that column right here, we want to turn it into the return. Okay, so here's the equation to go from rewards to returns. This thing right here. So I'm going to write down this equation in another way. In other words, the return equals the reward at the same time step plus gamma of the reward at the next time step. So here's 0, here's 0, here's 1, plus gamma squared at the next time step, and so on and so forth. So if I wanted the reward for the first time step, I would take my list and I would go through the entire thing this way, pulling them out and multiplying each successive one by a higher gamma. So let's write the pseudocode for how we would do it this way. This is a less efficient way to do it. But if this way makes more sense to you, I wanted to show it to you just in case you prefer it. So what the pseudocode for that will look like is that for I in the length of the rollout, then we're going to have to do a double for loop for I in the range of the length of the rollout. And then for I in the range of, no, for j, gosh, I'm bad at programming. For j in the range of I to the length of the rollout, then you say the return equals 0, and then here you say that the return equals, or plus equals, the reward at j times gamma to the power of I. So that would be how you calculate the return, and then you take all the other stuff, you do memory dot append tuple of the rest of the stuff along with the return. So there's your basic pseudocode for how to calculate it this way. But this is a less efficient way and, in my opinion, more prone to errors. So if it makes sense to you, go for it. But if you'd like to see a better way, let's talk about that better way. So here, we can factor out a gamma. And this will result in R naught plus gamma times R1 plus gamma times R2 plus gamma times R3, and so on and so forth. Now, instead of calculating the return going forward, what if we calculated the return going backwards? Well then, the return for the last element in this list is just that reward. There's nothing else. The return for the element above it is the return that we just barely calculated, plus times gamma, plus that one. And so on and so forth going backwards. So let's see how we would code this out. Pseudocode. We would say for each of the elements in the roll out going backwards, for each of the elements in the rollout, particularly the reward, we're going to say that the return equals the reward plus gamma times the return. Because right here, this return is t plus 1, and this return is the return of t. Okay, so then the only real question we have to answer right now is, well, when you're at the very end of the rollout, what is the return of t plus 1? Well, that return is 0 because you're at the end of the game. There are no future rewards. You cannot get checkmate after the game is over, so you cannot get rewards. You cannot capture pieces. The game is over. There are no future rewards. So we say that the return at the very, very end of the entire thing, after the last step, equals 0. Now this equation is true going backwards through the list. And then again, memory dot append all the stuff plus the return. For those that are wondering why we call it the return, you can kind of think of this like investing. Your reward is the sum of money that you are paid on a specific day. Like, your reward are your wages or something like this. And these terms actually do come from economics, by the way. So if this is the present time, these are your rewards for working on that day. And the interest rate tells you how much you would have to be paid in the future for you to feel like it was equivalent to be paid the lower amount today. And that's what we call the discount factor, gamma. So I would rather have $100 today than $1,000 in the future. That's called the time preference in economics. For us, we call it gamma. And so what that's saying is, if I'm going to get a reward in chess, 10 moves from now, that reward to me is not as good as getting the reward immediately. And so I'm going to discount it. You know, if I'm going to win a piece 10 moves from now instead of a move right now, I'm going to want it to be a queen instead of just a pawn, right? All things being equal, I would rather capture a piece right now rather than in the future. But I will go for the future if it's more valuable. And the preference I give to the present over the future is called gamma. So that is why it is called a return. It literally comes from economics, from interest. The return on your investment is the sum of all your future rewards. Okay, so there's the pseudocode for calculate return. It really isn't much pseudocode because Python is so dang simple. But there, yeah, so that's calculate return. Let's talk about learn PPO. And then we'll come back to get action PPO because I want you to realize something from learn PPO before we talk about get action PPO. For each epoch, for each batch, we have our 4 steps. Opt-in, 0 grad, calculate return, loss dot backward, sorry, not calculate return, calculate loss, loss dot backward, opt-in dot step. Okay, so here are the losses for the PPO. We have already calculated this equation here, so no need to worry about that. What we need to calculate is this monstrosity and this monstrosity. Actually, this one's not a monstrosity. This one's pretty simple. Okay, this is 1 over n. It's a mean of the sum of the difference squared. So it's a mean squared error. And it's a mean squared error between the actual return and what our value network is predicting the return is. So that's pretty straightforward. We would like our value network to be actually predicting the real return that we get. The return we're going to get out of the batch, and the V of S is the state passed through the value network. So we have, let's say, V equals, or V of S equals the value network given the state. And the state is a variable that we're going to get out of the batch. The batch is going to be a tuple of all of these variables. Okay, so there's VS, and then we're just going to take the mean squared error of that and the actual return. Now notice the advantage is the reward minus what we actually, the true reward minus what we thought the reward would be. So this value loss kind of is the mean squared error of just the advantage. So that's the way that I'm going to code it up. The advantage equals the return minus VS. And so loss value is going to equal the advantage squared dot mean. So there's the loss of the value. Super simple. Okay, so let's talk about the policy loss. The policy loss is the negative of the mean of the sum of the mins. There's a lot of stuff going on, so let's break this up into parts. The first part that I hope you recognize is that this pi prime of a given s shows up twice. So it shows up twice, let's just throw it into a variable. Let's call that whole thing a ratio. So let's say ratio equals pi prime divided by pi. So what is this exactly? Well, what this is saying is that pi tells us the action, the score for the action that we want to give. We're going to interpret this as like a probability distribution. What's the probability we should take each action? So pi prime of s returns an action distribution, but pi prime of a given s takes that action distribution and gets the specific action out of it, right? So we can say pi prime equals the new action distribution. And how do we get the new action distribution? We take our policy gradient, or our policy network, and we pass in the state, and that's going to get our action distribution. Out of the action distribution, we want all of the rows in the entire batch, and we want just the specific action that we took. And this action is also coming from this batch. So there's pi prime. But what's pi? Pi is the policy that we had when we were learning this. When we took this action for the first time, when we were exploring. So that's going to come out of the batch. So if you call it action distribution or something like that, well, we're going to take all of the rows of action distribution, and we're just going to take the columns that corresponds to the actual action we took. So there's pi prime and pi. Okay, so I just want to point out these might not be the correct shapes and stuff like that, but I'm not going to go through the exact specifics of the code. You guys know how to debug shapes and things like that. So the loss for the policy is going to be equal to torch.min. It's going to be the minimum of the ratio times the advantage, and torch.clamp the ratio to be between 1 minus epsilon and 1 plus epsilon times the advantage. Right? So that's the whole thing, and then we're going to take the mean of that, but you want the negative. You want the negative of this whole thing. So you add your losses up, and you call loss backward, and optim.state. Okay, so get action PPO, we need to get our action distribution. That comes from the network working on the state. You'll have to figure out if state is in the right shape or not. And then the specific action that we want is going to come from multinomial on the action distribution. Now look up the documentation for this, because I intentionally have not done the parameter list right. I want you to go look up the parameters yourself. And then you just need to return the action and the action distribution. Okay, this is right, but not quite. So I want you to realize that down here, when we calculate the ratio, we're using this action distribution that we're getting from right here, but we're also creating an action distribution on the fly. So what that means is that we're kind of using the network twice within the loss function. And so that's going to cause backpropagation problems. So what we're going to have to do here is we're going to detach the distribution of actions, which will also inherently detach this action, so that backpropagation cannot hit this network when it's supposed to be hitting this network, which are the same thing, by the way. These are the same network, but we don't want backpropagation to be hitting them twice, only once. Okay, well, since we're not supposed to be hitting this anyway, why don't we just do with torch.nograd, or however you spell that. You'll have to go look up that function yourself, because that's not actually how you spell it. And then all of this. Okay, so that's get action PPO. One other thing, the advantage also has the value in it, but after we calculate the value loss, we're going to be using the advantage here. And so we'd like to detach, we're using the advantage down here and right here. And so we'd like to detach the advantage as well as soon as we're done using it for the value loss. So advantage equals advantage dot detach. And I believe that's everything you need to know about the 3 PPO functions. Okay, good luck on your lab and have fun.